Welcome you all to the lecture on Zeeman effect. When hydrogen atom is placed in an external field, the energy levels shift. This is called Zeeman effect. To understand this, we need to understand how magnetic field interacts with electron spin. At the classical level, in the presence of vector potential, canonical momentum P becomes P plus Ea by C. The Hamiltonian is given by equation number 1. The sum in the above equation runs over all particles in the atom. In quantum theory, P, A, R are promoted to operators. The Hamiltonian operator is now given by H bar is H hat is equal to 1 sum over A 1 over 2m times PA plus EA hat by C whole square plus U hat. Since the atom has spin half electrons, the interaction of the magnetic moment with the external field has to be taken into account. For a particle with spin and magnetic field, we have A is equal to P plus Ea by C whole square by 2m plus mu over S times S hat dot B plus U, where S hat is the spin of the particle and mu is a constant. Expanding the terms, we get equation number 4. Since R and P do not commute, we have P dot A times minus A dot P is equal to minus I S bar divergence A. This can be verified using a test function. We can choose A such that divergence A is equal to 0. That simplifies the calculations. For example, A can be half times B cross R, with B being homogeneous isotropic field. Uniform, in other words, B has to be a uniform field. For an electron, mu is equal to minus E over m times S hat. Substituting this in the expression for Hamiltonian of an atom, we get equation number 6. The summation is extended over all electrons. U contains the interactions of the nucleus with the electrons and between electrons. Let H not be the Hamiltonian in the absence of field. We have equation number 7. Full Hamiltonian. Substituting the value of A, we get H equal to H naught plus E over 2mc times B dot sigma A or A cross PA plus C square over 8mc square times sigma over A times B cross A or A whole square plus EH bar over MC times B dot S hat. Now R cross P is the operator of the orbital angular momentum of the electron. Denoting the total orbital angular momentum operated by L hat, the Hamiltonian becomes equation number 9, where mu naught is equal to E times H bar over 2mc is called Bohr magneton. Weak field approximation. For weak fields, we can neglect the term quadratic in B. Now the term linear in B can be regarded as a perturbation to the eigenstates of H. The rotational symmetry of the unperturbed Hamiltonian has been removed by the magnetic field by choosing a direction. However, the axial symmetry with respect to the direction of the magnetic field still exists. Hence, the component of total angular momentum along that direction of the field is conserved. The, the amount of correction due to the perturbation can be obtained by taking the average of operator L hat plus 2S hat. Delta E is equal to mu naught times the average of L hat plus 2S hat times dot B is equal to mu naught times average of J plus S dot B. If we take the direction of magnetic field, if we take the direction of the magnetic field to be the z-axis, we get delta E is equal to mu naught B times Jz plus Sz. In the unperturbed state, J is conserved. The measurement of spin gives the average value since it is not conserved. The only direction available is the direction of the total angular momentum J. Hence, S bar has to be proportional to J. Since J is equal to L plus S, S dot J is equal to J bar dot S bar is equal to constant times J square. Thus, S bar Z is equal to Mj times J dot S divided by J square. Now, J dot S is equal to half times J plus 1 minus L times L plus 1 plus S times S plus 1. We can now obtain the full expression for the energy splitting as equation number 13, where G is called the Landau G factor. Splitting at the unperturbed energy level is called Zeeman effect. If S equal to 0 equal to L, J equal to 0, hence Mj equal to 0, linear perturbation by the magnetic field vanishes. In this case, the third term, that is quadratic in B, contributes. The shift in the energy levels is the average of this operator in the unperturbed state. That is given in equation number 14. Now, B cross RA is equal to B times RA times sin theta, where theta is the angle between B and RA vector. Since sin square theta bar is equal to 1 minus cos square theta bar, since cos square theta d cos theta is equal to 1/3, the above average becomes delta E is equal to E square over A times C square times B square times sum over A RA square. RA square. Now delta E now minus uh, minus minus del delta E divided by delta B is the magnetic moment acquired by atom in the magnetic field. Denoting this as chi, we get chi is equal to minus E square by mc square times sum over RA square, or the atom is diamagnetic since chi is negative. For j equal to 0 but s equal to L not equal to 0, the linear term again vanishes. But in this case, the second order perturbation theory needs to be used and it dominates the term quadratic in the magnetic field. Thank you.